And it is now 7 o'clock, so we're going to officially get started. Welcome everyone to 60 Minutes in Space. All right, I'm seeing a few more people are coming in, so I will give a slightly slower introduction just to make sure everyone can join us before we begin. So welcome to 60 Minutes in Space. This is a program we've been doing at the Denver Museum of Nature and Science for many years, where we invite people to come and hear from real working space scientists about what's new in space science. And we're going to start right now. So to begin tonight's event, I'd like to introduce Dr. Jessica Libby-Roberts. Dr. Libby-Roberts earned her PhD in astrophysics from the University of Colorado Boulder and is now a postdoc at Pennsylvania State University. She's an avid planet hunter and is working to discover new planets around other stars and study their atmospheres. She's particularly interested in the very weird superpuffs, planets that are so fluffy they have densities similar to cotton candy. So, all right, take it away, Dr. Libby-Roberts.
Thank you for that introduction, and hello, everybody, and thanks for joining for tonight's 60 Minutes in Space. I'm really excited to be here and maybe not get a chance to present on my own research, but a chance to talk about some really fascinating things that have been happening in astronomy over the last month. So to get started, I'm going to share my screen here. All right, so I'm going to work on the fact that unless somebody comments, I'm going to assume you all can see my screen. And so tonight, I will be talking a little bit about exoplanets or planets around other stars. I am a planet hunter. I go out and I search for planets and try to find them. But before I actually talk about those exoplanets, I actually want to talk about something that has, well, it's already been touched on in the 60 Minutes of Space. I know last month, Katoon did a wonderful discussion about what JWST is and the technical specifications and what all went into launching this telescope. So tonight, I actually want to review a little bit about JWST, but then also talk to you what it has been doing over the last month. And the reason why I want to spend so much time on JWST is this telescope is just going to go and do awesome science. And my guess is that you will be hearing about JWST for many years, hopefully, in this 60 Minutes in Space as it makes different and new and exciting discoveries. In fact, JWST is really poised to revolutionize astronomy as we know it. It is going to give us new insights into the universe, and we are going to see our galaxy and other galaxies in new perspectives. And I know that it's going to revolutionize astronomy as we know it because we've already witnessed a similar revolution with the Hubble Space Telescope. So Hubble was launched in the 1990s. Well, it was actually launched in 1990, and for the past 32 years, it has been making incredible number of discoveries. In fact, and I'll talk about this, a recent discovery just came out this morning that Hubble made. Now, Hubble has revolutionized the field of astronomy so much that my guess is that everything you know about astronomy has probably been impacted by some type of Hubble discovery. And if that's not enough, I would wager to guess that every single one of you here has seen a Hubble image of some sort, whether it's the famous pillars of creation, a galaxy, or even our own solar system. And if you're out there shaking your head saying that you have never seen a Hubble picture, I will prove you wrong because my background is actually a Hubble picture. So now everybody here has seen an HST image, and these things are just fantastic to look at. So how successful is Hubble? Well, NASA released for its 30-year anniversary this image of the night sky. And each one of these dots that I'm showing you here is a region of space that Hubble has looked at. And the color of those dots corresponds to what type of object it looked at, whether it was a star or a galaxy or even a planet. But what's important about each of these dots is that, well, Hubble has basically covered the entire night sky. It has been that successful. But with Hubble, it's a little bit older. It still limits. It has some issues. And NASA was actually aware of these limitations. It knew of its successes and its limitations. And so in the mid 1990s, it actually decided that we wanted to build a successor to Hubble. We wanted to capitalize on the success Hubble was having and also try to overcome some of those limitations that Hubble was experiencing. And so their first idea that they wanted to build for this telescope, which would later be named the James Webb Space Telescope, or JWST, was we knew we wanted to build a bigger mirror. And we didn't just want to size up the mirror ever so slightly. No, Hubble or NASA was ambitious. They wanted to create a much bigger telescope. And to show you how this looks is I'm showing, hopefully everybody can see my mouse here. Here's Hubble, this gray disk, which is a little over 2 meters in diameter. JWST, on the other hand, is a whopping 6.5 meter telescope. This thing is about 21 feet across. And the reason they wanted to make JWST bigger was because a bigger mirror means that we can see fainter objects. It also means that we're able to reobserve some objects that Hubble looked at, but in finer detail. So this is sort of the idea of successor, but NASA didn't want JWST to compete with Hubble. They wanted these two telescopes to work together to try to understand the universe. And so to complement Hubble's wavelengths or light that it was able to observe, Webb looked in a whole different regime of light. So Hubble looks in the visible. This is the light that you and I can see when we look outside or just open our eyes. Hubble also looks a little bit in the ultraviolet regime. This is the wavelength of light that gives you sunburns, and a little bit in the infrared. JWST, on the other hand, is going to look much further into the infrared. And so that's what I'm showing here. Here is Hubble's range compared to JWST as it moves out into the infrared. Infrared wavelengths of light is the same thing as heat. You sitting there at 98.6 degrees Fahrenheit are emitting infrared wavelengths of light. We just can't see it with our own eyes because our eyes are not adjusted to that wavelength of light. This means that JWST, when it stares out at the universe, is actually seeing the universe in ways that our own eyes could never perceive, which is it's just really awesome. And so why we wanted to look in the infrared, this was actually chosen on purpose. And it is because infrared complements the visible. So an example of this is this image of this galaxy taken with Hubble, or HST, I'll sometimes call it. And you'll notice on the left in the visible, as this is taking, we see these dust lanes that are just not apparent in the infrared. And that is because dust absorbs and blocks visible wavelengths of light. This means that if we wanted to study dust or see where the dust was in a galaxy, the visible wavelengths of light is great. But if we want to actually see the stars behind that dust and study the galaxy at its center, then we need to move to the infrared, which is wavelengths of light that the dust doesn't actually absorb. In fact, it's quite transparent, and so we're actually able to see through that dust and the stars behind it and learn something new about this same galaxy. Another reason we wanted to go to the infrared that I'm particularly excited about being a planetary scientist is that planets emit light in the infrared. Everything that has a temperature of some sort emits some type of infrared, and it just so happens that planets are fairly bright in the bandpass that JWST is looking at. So this image that I'm showing to you here of Jupiter is that in the infrared. The normal image that you see of Jupiter, the one with the great red spot and those brown and white bands, are as actually invisible light. And that light is due to the sun emitting that visible wavelength of light. It hits Jupiter. Jupiter then reflects it back to us. Instead, in this infrared light, this is actually light that Jupiter is creating itself. And so this gives us a chance to study planets, study the light of planets where we don't have to rely on the star's light to bounce off of these planets. While this is exciting that we can now see planets in the infrared and their emission of light, It also means that Earth emits its own infrared light. So we can't put JWST in orbit around the Earth. If we were trying to do that, that would basically be similar to trying to take a picture with a spotlight shining behind us. It just contaminates any image that we would try to see, especially since we're trying to look out into really the darkness of the universe and trying to get fine details. So this meant that we needed to put JWST far away from the Earth, but not too far that we weren't able to communicate with this telescope. And so this is why it was decided to move JWST beyond the orbit of the moon out to this so-called L2 point. It also meant that this distance is so extreme and so far away that we had to get JWST right on the first attempt. If something were to break on Webb, it means that we aren't able to send out a crew to go fix the telescope. And this is in part why there were so many delays coming from when JWST was first proposed to over 20 years later when it finally was able to launch. We had to be so careful about everything we did with JWST and make sure it worked perfectly. So not only did we need to make sure JWST arrived at this point, this L2 point, but during its two-week or so mission out to the L2 point was that JWST would actually need to unfold. And for some reason, there we go. Oops, there we go. And the reason why we needed to unfold JWST was it's so big, we had to fold it up to fit it into a rocket. So over those 2 weeks or so, as it made its way out to the L2 point, it had to unfold itself so that it could eventually take the images that we wanted it to take. And so this was a very, I would say, nervous 2 weeks for many of us astronomers as we waited to see if something broke or if it worked perfectly. And thankfully, as far as we can tell, everything worked just like it was supposed to. And that's sort of where Kachun left you last month, was JWST had just taken its first image, and its first image had looked something like this. Now, this is kind of a chaotic first light. And in fact, each one of these points is actually of the same star, but the same star as observed by one of JWST's 18 smaller segmented mirrors. So I'm showing you a picture on the left of what JWST's mirror actually looks like. And you'll notice that it's one large mirror composed of 18 little individual mirrors. And so each one of those stars corresponded to one of those mirrors. And the reason why they're all scattered all over the place is because Webb still wasn't in alignment. It wasn't focused. So over the last month, Webb has really been working on aligning itself in order to take its first in-focused image. And so to align itself, it performed two separate ways to do this. The first one was, I think, sort of a neat idea. It used the camera on board, which was called the Near Infrared Camera, or NIRCam. And it used this camera to align each of its mirror by using a special optic, which enabled NIRCam to basically look down on Webb. And so you're looking at the primary mirror itself. And you'll notice from this first image that Webb looks very much out of focus. And that's probably because the telescope was out of focus. And the other thing you'll notice is that this one panel, I don't know why, sorry, there's a delay in my flipping through the slides, but you'll notice that there is this one panel that seems to have lit up. And the reason why this one mirror panel has lit up is because this panel has been focused and aligned properly. That means that the star's light is coming down, it is hitting that mirror, and it's bouncing into NIRCam's lens. All these other mirrors are bouncing the star's light in every direction but towards the camera itself. So it played this game where it tried to light up all of these different mirrors. And in the end, NASA just released JWST's first real selfie. And I kid you not, this image is actually real. It looks very much like a computer simulation or a cartoon, but this is actually a real image of JWST's mirror looking down from NIRCam. And so every one of those panels has now been lit up, which means that it's focusing all of the starlight up into NIRCam's lens. And you'll also notice that those lines are actually quite sharp. Like we have focused this telescope well. Nothing is very blurry. But it didn't just look at the telescope in order to make these alignments. It's also looked out at its field of view. And so how it aligned itself from its field of view is we started with that image that I had previously shown you, and NASA worked to figure out which of those stars correspond to which of those 18 mirror segments. And then once it knew which of those stars correspond to each segment, it was able to move these stars so that it appeared in a pattern that we recognize, where each of these dots corresponds to those correct segments. It then took those blurry images and did the best it could to focus each individual segment so that we now see a fairly solid point of light. The next step from getting that solid point of light was to move each one of those stars onto the secondary mirror, that mirror that's above the primary mirror. So over here is that secondary mirror. And this is actually a simulation of exactly what moves were made in order to move each of those stars onto that secondary mirror. It started with the inner segments were slowly pieced together, and then the outer dots came together at once. And you can see that once everything was aligned, that this secondary mirror lit up, and all that light was then tunneled down into the instruments. And so this was an amazing technological feat that NASA was tweaking all of these things and had to tell JWST what to do in order to get this focus. But they were very successful and finally released the first in-focused image from JWST. And that is of this fantastic star called 2MASS J17554, so on and so forth. This star is such a boring star that it doesn't even get a fancy name. In fact, it is currently enjoying its brief moment of fame, and then we will probably all forget about it. But we wanted to look at a nice ordinary star to focus because we didn't want anything wonky that was occurring would be occurring because of the telescope and not because something about that star. And so when NASA released this first image with great, like, we did it, guys, we have a focused image, you'll notice that maybe it's not as focused as we thought, because there are some really funky spikes going on. In fact, there seem to be 6 main spikes and sort of a horizontal fainter spike that's coming out of the star. And we know that unless this star has just not spherical and has decided to grow some points, that something must be going on in this image itself. And what you are actually seeing are what are known as diffraction spikes. And in fact, these are actually an artifact of telescopes. They're also an artifact of anything with a lens. So like your camera can also give you diffraction spikes. If you go out later tonight and you try to take a picture in the night sky of a street lamp, for example, you should see diffraction spikes, maybe not in this pattern, but you should see spikes coming from that light. And that is, well, it's simply because of physics. And it's because light is both a particle and a wave. And in this case, light is acting like a wave. So to think about how these diffraction spikes work, we're going to sort of dive a little bit into the field of optics and physics. And instead of thinking about light being a wave, let's think about water and water waves. That's a little bit easier, I feel like, in my mind, to think about waves and what's going on. So this is actually an image of a tank. We're looking down from the tank, and they have made a little motion, which has caused these waves to move outwards along this path. These waves then eventually hit a wall, and this is very similar to, say, light hitting and bouncing off of a mirror. And when these waves hit this wall, those waves are then reflected into sort of this weird pattern. And this pattern actually is very dependent on what type of wall it's hit, what the shape of that wall it is that the wave ran into. And this pattern is known as a diffraction pattern. So this is sort of a 1D flat wall example. But now let's move this now, thinking about this in 2D of a mirror. And let's think about a mirror that's very spherical. And so when light hits a very, very spherical mirror and bounces off, it actually creates sort of these ripple-like wave patterns in the image. So this is an image of light hitting the mirror, and then what we see in the actual camera itself. We see these sort of diffraction ripples, or this diffraction pattern. But JWST is not a spherical mirror. In fact, it's actually quite complicated. So if you think about it, JWST actually has multiple little components, and each one of those components contributes to creating a different diffraction pattern. So a hexagon, or those individual mirror segments, is a hexagon, or a six-sided, remember six-sided, just like those 6 spikes, mirror. And then after that hexagon, we also have to consider the fact of the combined mirror shape is also a hexagon shape. And then those multiple segments make up that hexagon shape. And lastly, we also have those beams that are holding up the secondary mirror that are also getting in the way of that light that's trying to hit that primary mirror. And those also create diffraction patterns because light is also hitting and being bent around those beams. But we're very good at diffraction patterns. And in fact, we were actually able to predict what each of these segments would do in terms of that diffraction pattern. How would each of these segments manipulate or bounce light around, and what type of ripples of waves would be formed for each of these? So you'll notice with the hexagon shape, we see that 6-pointed star. And you'll see that as it gets more and more complicated, we still see those 6-pointed stars, but it gets a little bit more complicated. But what's interesting is that once we add that third beam, or those 3 beams, we then introduce sort of this horizontal spike. And so this was not actually taken a picture of JWST. This was simulations that were done back in 2007, before we even looked through JWST's camera. So we knew going in what this diffraction pattern was actually going to look like. And the fantastic thing about it is that our image actually looks exactly like, or maybe arguably even better than, our prediction. This telescope is so in focus that we're actually doing slightly better than the predicted diffraction pattern. So this is why we have diffraction spikes. It's not because of the telescope not being in focus. It's simply because we are stuck obeying the laws of physics. And if we wanted to remove these diffraction spikes from the telescope, on the telescope side of things, we would essentially have to break the laws of physics. We would have to make light not act like a wave. And in the end, that would be very bad for us. So we probably shouldn't try to do that. Instead, we can try to remove these spikes with image processing systems, but there's a little added problem when you start to try to remove spikes. And that's, you're trying to take these images for science purposes. And once you start manipulating the image, you start changing it. And you can actually change your scientific results that you're trying to capture from this image. So in reality, it's probably not the best to try to remove these spikes unless it's actually scientifically necessary. And a little bit later in the talk tonight, I will explain one reason why it might be scientifically necessary. But there's sort of a neat way to think about this. I saw this on a YouTube video, so I'm going to shamelessly copy it and share it with you, is that it was proposed that this spiky image is actually a fingerprint of JWST. This is JWST's calling card. So as you go forward, anytime you see an image that seems to have a diffraction pattern like this, you will know that it was taken by JWST. So that is the star in and of a nutshell. But what I'm very excited about this image is not actually the star. I mean, yes, it's great. JWST has been focused. That is very exciting for the science that will come. But there is something so incredibly unexpected in this image. And that is that when we picked this star, NASA picked the star because it was supposed to be an empty space. There wasn't supposed to be any companions nearby. No objects. And we wanted there not to be any objects because when we were trying to align it, we didn't want to accidentally have an object mess up our alignment process. But what we discovered when we were trying to do this alignment is that the star isn't in empty space. It's actually has these blobs all over this image. And I only circled a couple of these because I realized that this would take me forever to try to actually highlight. But there are these circles, these blobs of light everywhere behind the star. And in closer inspection on each of these blobs, we discovered that these are actually galaxies. And not only are these galaxies, we are now seeing these galaxies at such fine details. And we weren't even trying with JWST. So what I'm showing, these images that I'm showing to you, I haven't done any special image processing. All I've done was tried to zoom in on that picture I just showed you to take a closer look at what was going on with those blobs. And in doing so, we are seeing galaxies with spiral arms. We are seeing on the far right, galaxies that appear to be colliding into each other. We're witnessing galaxy clusters, which I'm showing over here. Or even on the far bottom left, you can almost make out this bar look and these spiral arms. And these are only 5 little blobs that I picked. So I really encourage you after this talk to go and find this image. Just look up JWST first star image or something like that. And zoom in on each one of these blobs and see what you're able to find, because I didn't realize until I started doing that just how awesome each one of these galaxy pictures are. Now, this isn't a surprise that we are seeing galaxies. In fact, that is actually a discovery that Hubble has made. Hubble has already told us that there are probably trillions of galaxies out in our universe. What I'm showing here is an image from Hubble. This is a deep field image. Hubble basically stared at the same patch of sky for off and on for 10 days. And it compiled a bunch of these images, and we stacked those images on top of each other. And we came up with this spectacular mosaic of all the different galaxies that it saw in this small region of space. And the other thing I just want to point out before continuing is if you look at the star down here, you'll notice that it's got spikes and it has diffraction spikes. So Hubble also has a calling card in the form of 4 diffraction spikes. So fun fact there. But going back to the galaxies, which I think is the coolest part about this image, is that we knew that there were galaxies out there, but this was an image where Hubble was really trying to capture these galaxies. Instead, JWST was really trying to take a picture of this star, and instead, in 35 minutes, managed to capture all of these galaxies. Not only that, but NIRCam wasn't working at its optimal capabilities. So all the instruments on JWST, they get warm, they emit heat. That heat can contaminate our pictures. And so we have to cool down those instruments in order to suppress their infrared wavelengths of light. So when NIRCam took this image, it still wasn't fully cooled down. So you could almost argue that this image that we're seeing on the right from JWST is actually a fairly noisy image. There's still a little bit of contamination, background contamination from NIRCam. And so going forward, we're likely to see even better pictures than this, which is just very, very exciting to see. So what's next for JWST? Well, right now, JWST is currently testing all of its instruments. It's making sure that nothing's broken and that all the instruments seem to be working. But after that, for the next, starting in June and going to about September, JWST will be doing what is known as the early release science. So NASA asked about 5 years ago, it asked the community, what types of science would you like JWST to do first that both did science, but also tested the instruments? So you could test the instrument capabilities to determine, do they actually work for the science that you are proposing? And so multiple proposals were submitted, and I'm only highlighting a handful of the few that were accepted. And so over the next couple of months, JWST will be doing science from everywhere from imaging exoplanets and characterizing their atmospheres to looking in our own solar system, taking a good look at Jupiter and its moons. It's going to then move to the first galaxies. It's going to look out as far as possible as it can and look at some of the first galaxies and try to understand how basically matter in the universe formed, which is not my area, and that is so cool. It's also on its way to catalog a bunch of galaxies. I would say that that first picture is a good start, even though it didn't mean to do that. And then it's also going to try to study some of the oldest stars in our galaxy. And these globular clusters are what I'm showing on the far right. These are essentially not quite galaxies, they're just sort of a ball of stars. And so they've never really formed into a galaxy, and these balls of stars sort of orbit our Milky Way. So it's actually going to characterize these stars to try to figure out basically how they formed. So this is all of the science that is going to be done, and it's all going to be done by September. So as I was saying, in 60 Minutes in Space, you'll probably be hearing a lot about JWST. The other really exciting thing about all of this early release science is that NASA is going to make all this data public as it comes in. That means that if you are feeling like you want to look at some JWST images, it is available for you to look at. And then I put this, and then the science begins, because keep in mind that while all this science is being done, we're also testing the instruments. But then once these instruments have been tested, a whole new slew of science is going to happen. And this is just, there's a lot of science to be done and a lot of science that will be coming at you soon. So I personally cannot wait. I also want to point out that when JWST was first planned, it was thought to be a 5-year mission, which really had us astronomers wondering how we were going to pack in such science into 5 years. But one benefit from that delay, that 2-decade delay, is that our instrument, our technology advanced. And it advanced in a way that we could maintain these instruments for much longer than 5 years. In fact, it is now predicted that as long as nothing catastrophic failure occurs in JWST, either from the instruments or the telescope, that JWST could last for more than 20 years doing science. So in this way, this is another way it's going to become Hubble's successor. Just like Hubble did decades worth of science and continues to do I don't know if it will continue to do decades worth of science, but it continues to do science. JWST is potentially to go do another decade worth of science or more. So that's very exciting. And I want to take a moment to pivot from JWST, because it's going to do all of this great science. And I mentioned that how the silver lining of that delay is that it allowed us to basically become a little bit more technologically advanced. It also meant, as an exoplanet scientist, it gave us a chance to go out and find more exoplanets. If JWST had launched when we had predicted it to launch back in 2010, I believe, there was only a handful of planets that we knew of. And that meant that we weren't going to have very many planets that we could characterize. But now we have just come out and said that we have now discovered over 5,000 exoplanets in our galaxy. In fact, we have found so many exoplanets that we're pretty sure that there are more exoplanets in our galaxy than there are stars. And there are billions of stars in our galaxy. So think about just how many more planets are out there to find. And if I look at it, I also think that that's some good job security for myself. But what NASA has done with these 5,000 exoplanets is it has taken a new way of visualizing what these planets look like. And it's done so not visually, but by sound. So what they did was they decided to play the discovery of exoplanets over time, but assign a sound to each one of those planets. And the pitch of each of these tones varies based on the orbital period of a planet. Planets that are discovered very close to their star have a higher pitch, and planets that are further away from their star have a slightly lower pitch. So I want to play this video to sort of highlight how these discoveries are made and just how musical this discovery is. I also want to point out on this video that each one of these circles that you will see is a location of where that exoplanet was found. So this might be a little bit faint, so you might need to turn up your sound just a little bit when I play this. So there's our first two exoplanets. So if you want to turn down while I talk, if you already turned it up, but that I think is a nice way of visualizing all these exoplanets. And I also want to point out that there's a patch in the sky over here, and that's actually where the Kepler Space Telescope was staring for about 4 years and finding a bunch of planets just in this one little patch of the night sky. And that's why that area is just all lit up. What's great about 5,000 exoplanets, oops, let me see if I can move this forward. What's great about 5,000 exoplanets is we're no longer concerned about individual planets. We can start actually doing some statistics. We can start trying to build a bigger picture of what these planets tell us about all sorts of solar systems in our galaxy. And what I mean by that is if I plot those exoplanets on a graph such as this, I can start to see little trends that begin to appear. And so what I'm plotting on the y-axis is the planet size in terms of Earth radii. So 1 Earth radii would be the size of the Earth. 11 Earth radii is the size of Jupiter. And I've marked those cuts on the right for Jupiter, Neptune, and Earth. And then on the x-axis, I'm plotting the orbital period, or how long it takes a planet to orbit its star. And keep in mind that this is on a log scaling and in days, but I've marked for reference on the top the orbital period of Mercury, Earth, Jupiter, and Neptune. And you'll notice a couple of unusual things that start to pop out when you plot this. And the first one is that there are a lot of planets out there that are much closer to their star than Mercury. Mercury is the closest planet to our own sun, and yet it seems that it's quite common to find planets much closer than that. In fact, there's a certain population of planet that jumps out here. And these are these gas giants, these Jupiter-sized or bigger planets that seem to orbit their star in just a handful of days. This is actually the first type of planet that we discovered around a sun-like star. And at the time when we discovered this, it was, we were a little hesitant to declare this was a planet because this was so surprising. But now we know that while hot Jupiters aren't common, we know they aren't rare. But the question now remains is, why doesn't our own solar system have a hot Jupiter? And how do you form these Jupiters? Does it form very similar to our own gas giant and move inwards? Or are these planets that just happen to form so close to their star? The other interesting feature on this in this plot is that these planets that are somewhere between the size of Earth and the size of Neptune, which are dubbed sub-Neptunes or super-Earths, seem to be the most common type of planet in our galaxy. Now, in our own solar system, Earth is the largest rocky planet. All other rocky planets are smaller than our own planet. And Neptune is our smallest gas giant, with all other gas giants being larger than Neptune. We have no planets that fall within this radius, and yet the galaxy seems to be very good at making these types of planets. Again, leaving us to wonder why we don't have any of these types of planets in our own solar system. In fact, of those 5,000 planets that we have found so far, we have yet to find a single system that looks the same as our own solar system. For some unknown reason, our solar system seems to be the oddball when it comes to exoplanets, not the other way around. The other feature is not where the planets are, but where there aren't any planets. And there's this huge gap about Jupiter-sized and smaller, and planets that fall about the same period as Earth, so taking about a year to go around their star, or taking longer. So we found 5,000 planets. There's hardly any in this gap. And the reason is not because there aren't any planets that exist in, or that there aren't any planets to exist in this gap, but it's simply because it is much harder to detect these planets. It's hard to detect small planets because their signal size is much smaller. And it's also harder to detect longer period planets simply because, well, it just takes more time to observe as you wait for the planet to orbit its star. So of those 5,000 exoplanets, think about it as we have found the easiest to detect exoplanets that we know of. Now it's time to beef up our instrumentation and try to go after these harder planets to find. We want to know how many planets are out there. You know, maybe sub-Neptunes and super-Earths aren't actually that common when we start to expand and look at periods greater than a few days. And so JWST is actually going to help with this effort. It's not going to fill in all of this gap, but it's going to make a valiant attempt to find Jupiters and Saturns around that orbit their star with periods greater than that of Jupiter. There we go. Sorry, there's always a delay. I don't know if you're seeing the delay on your slides, but there's a delay on my slides. So what I'm circling here is JWST and where it will actually detect planets. And so it's going to start filling in this gap, maybe not all the way down, but at least it's going to provide some much needed information about exoplanets and exoplanet formation. And it's going to do this in a really neat way. It's not actually, it's going to image the planets directly. It's not going to rely on methods like the transit method or radial velocity. It's going to take pictures of planets. And the reason for that is I'll show you an example here. This is actually directly imaged planets that we have seen with Spitzer. And how it's going to do this is it's going to block out that nicely focused star. And it's going to remember that planets are very bright in the infrared. And so when we block out that star's light, these planets should just pop out. These planets are very bright in the infrared. And as long as that star is not overwhelming them, we should begin to start seeing these planets. And so this is how JWST is actually going to find these planets. And this is what's very exciting. It's true that each one of these planets is going to make up about a pixel, but so we won't actually be able to see like individual features on that planet, but we'll still be able to obtain their spectra and learn something about what their atmospheres are made of. There we go. Okay. So that is exoplanets up with JWST. But I just want to pivot a little bit and talk about one last thing that just was released today. And so bear with me because this came out just this morning. And so I kind of scrambled to put these slides together, but I think it was very exciting and I just wanted to share it with everyone. And that is that Hubble, not JWST, Hubble has continued to make discoveries. In fact, Hubble has now found the oldest star in the universe. And what I'm showing is this very large picture from the press release, and each one of these blobs is a galaxy. So just like that JWST image or that Hubble image, we know that most of these blobs are galaxies. But what researchers discovered was there's this odd band of red light. And they took a closer look at this odd band. That's where the arrow is pointing. And again, these are early galaxies, but what they wanted to focus on was this red band of light. And it turns out that this band is actually a star that has been, and I'll talk about how it works, but it has been stretched into this ring. And when they looked at the closer inspection, you can kind of make out this point where the arrow is pointing of the star. And it turns out when they looked at the star and they measured its wavelength, they discovered that this star is actually about 12.9 billion years old. This star formed when the universe was 900 million years old. That means that this star may be one of the first stars to have ever formed in our universe. So studying this star will very much give us information about the type of environment that the early universe, what the early universe was like. But it looks like a ring, not a point. And how did they go about seeing this star? It's very faint and far away. And this is again because of physics. And so I'm going to attempt to explain general relativity in 30 seconds. So bear with me on this. Now, light is a wave, and as a wave, we know that when it hits things, it bounces back in a wave pattern, but we also know that light bends around objects. So this is in a simplified way. Think about if you were to watch a stream, and you're seeing the ripples of the water as it makes in the stream or the current. Now you put a giant object like a rock right in your stream and you watch the wave, and those waves of light or waves of water are going to bend around your rock and come out the other side. That means that if you had information on some of that water that was right behind the rock, as it bends around that rock, then you'll actually be able to see what was hidden behind that rock. So the same notion is here. If we have a star that is behind a massive object like a rock, but in this case, galaxies, that light is actually going to bend around that galaxy, just like that rock and for water. And we're going to actually be able to see it being bent around in the form of different images. So showing how this gravitational lensing looks, you can see that this is actually behind the galaxy. And now, but when we see it, we're actually seeing it in multiple locations because of that light being bent. The same idea holds this is showing points. The same idea holds for why we see it as a ring. And that is because light isn't just being bent going up and down and east and west. It's being bent all over. And so because of that, if you put it at just the right location, this bending of light is not going to give you just a couple of points. It's actually going to form this ring structure because the light is being bent in all directions. And not only is this light being bent, it's also being slightly magnified. So it's actually making the object appear brighter to our own eyes. And this is what is known as an Einstein ring. Or in the press release, they called it a critical curve. And so that is what's happening with this star. This star is actually behind a bunch of galaxies, but it's being bent and magnified to the point that Hubble is actually able to see it as a ring of light. What's also really awesome about the star is not only were they able to figure out that the star is about 12.9 billion years old, but they were able to approximate its mass. And what they actually found with this the star's mass is it's massive. It is about 50 times the mass of the sun. It's also very bright. It is outshining its own galaxy that it's in. In fact, they think that the star is about 1 million times brighter than the sun. And this is what we expect from the early universe. In the early universe, everything was very compact. And so it was very easy to obtain a lot of hydrogen helium when you're trying to build as a star. As the universe starts to expand, you start to spread out all of that hydrogen and helium. And so it's not as easy to try to eat away at all that hydrogen helium. You have to just, whatever you can get your hands on, if you're a star, is how big you're going to form. And so this is a press release that they just put out. And while Hubble, you can see it's very grainy, but imagine what JWST can do with the resolution that we just saw in those galaxy pictures, now when it actually looks at the star. And while it hasn't been confirmed yet, my guess is that this is going to be one of those objects that JWST will look at in the first year of its observation and maybe tell us what the star is made of, which then in turn can tell us basically what the universe, simplified, but what the universe was made of, how was it composed 900 million years after it initially formed. But this also means that JWST has an ever-growing to-do list. So if you think your to-do list for tomorrow seems pretty long, just think about what JWST needs to set off to accomplish. So it's going to do everything from studying planets. It's going to go out and find planets. It's going to go take a look at nearby stars and galaxies. It's going to look at faraway stars and galaxies and hopefully tell us what the universe was like right after the Big Bang. It's going to attempt to answer the question of, are we alone in the universe? And then the follow-up question of why we are here. Now, there's no guarantee that JWST will actually answer these questions, but it's going to try. And I'd like to say that pretty much to sum up JWST's to-do list is to find that answer to life, the universe, and everything. And hopefully it ends up being something a little bit more than 42. So I'm sorry for those of you that did not get the joke, but hopefully a few of you did. But with that, I will close here and I'm more than open to taking questions. And you can ask me questions about anything I talked about right here today, or any questions you might have about astronomy in general. And I also want to emphasize that there are no dumb questions. We're all here to learn, and I will take whatever and any questions. So please ask away. Thank you.
All right, thank you so much. That was absolutely wonderful. Wonderful presentation, and we already have lots of questions. We are getting close to 8 o'clock. If people need to leave because it's a school night, we totally understand. But if you want to stick around, we do have some time for some questions. So right off the bat, we did have one person asking, what is an exoplanet?
That is always a fantastic question. So an exoplanet is any planet that orbits a star that is not our sun. It doesn't matter how big or how small. It just has to orbit another star, and that makes it an exoplanet.
So this kind of answers this question, but still, have we found any exoplanets or bodies like that that do not orbit stars?
Actually, yes. And good follow-up question, because you are totally correcting what I just said. We have found quote unquote rogue planets is the name. And these are exoplanets that at one point formed around the star, but during its formation, there was gravitational interaction with other planets in that system. And eventually one or more of those planets gets kicked out of the system. And so these planets are sort of free floating the galaxy, going wherever they want to. And they're not actually tied to any planet or any star, which is why they're known as these rogue planets. And we have found, I believe, more than a handful of these.
Very cool. Very cool. Okay, so oh, so many good questions. Let's see. Is NASA already deciding the next generation telescope? Are they already working on that?
Yes. Yeah. So they actually just a couple of months ago released what will be the next, well, JWST's successor. And it is this, oh, it's not called Louvoir anymore. I forgot what they're actually nicknaming it, but it's going to be a bigger telescope than JWST. I believe it's 8 meters, though I know there's astronomers on this call who correct me. I'm blanking on the size, but it's going to be a lot bigger. And it's also going to look at a wider range of wavelengths. So it's going to look at UV more so than Hubble is, all the way down to infrared. So not only are we going to look at the wavelengths of JWST, but we're going to see Hubble and then yet to be explored wavelengths of light. And this is set to launch in 20 years or so, but it's already being thought about and planned and budgeted for.
Very cool. No resting when you're a space scientist. Charlie, age 5, would like to know, did the Big Bang make sound?
Oh, that is a good philosophical question. So for sound to be created, it means that whatever is creating that sound needs to run into things. It needs to run into molecules to transmit that sound. This is why in space, when there's no molecules around, you technically can't hear anything. So whenever you watch a movie and something blows up in space and you hear a big boom, that's not actually true. It's actually very quiet and silent. And so since the Big Bang, when it came into existence, probably there was nothing there for it to create a sound. So it probably didn't create any sound, just probably a brilliant flash of light. And then the universe was there.
Very cool. So you mentioned that JWST is at L2. Why L2 and not L1 or L4?
Yeah. So L stands for Lagrange points. And L2 was picked. I'm not going to try to move back my slides because my computer is not working. But so L2 was picked because in part, it's much further away from both the Earth and the sun. So that already helps. We also want it to be, if you move, so L1 and L3 are slightly closer to the Earth or on the other side of the orbit between Earth and the sun. And that's not great because that's a lot of infrared light that's being produced. L4 and L5 are in Earth's orbit. They're just further away. And the issue with there is that, again, you're still closer to the sun than where L2 is, but you also want to be able to communicate with Earth. And L2, I believe L2 is just ever so slightly closer. So if that makes sense, we're further from the sun and that light pollution, and yet we're still able to talk and control what's going on.
Yeah, that makes a lot of sense. Thank you. So how rapidly can JWST turn, say, to look at Jupiter and then to look at something far away?
I don't actually know off the top of my head for how fast it can turn. I do know that observations are planned about a year in advance. So they are currently scheduling what JWST will look at for the next year and a half. And the reason they want to do that is because they want to stack up observations that are near each other. So if we looked at Jupiter and then we wanted to look at something a little further away, we just want to kind of slew the telescope. And the reason we don't want to spend, or we want to keep things close, is because JWST does have a limited amount of fuel. And so if we're doing fine-tuned corrections as we do this, we don't want to use up too many fuel. We don't want to look at Jupiter and then slew all the way back here and then all the way up here. We want to conserve as much as possible. So my guess is it will turn fairly slowly because we want to be cautious, but I don't actually know how fast it will be moving. But anything that it looks at has already been preset before.
All right. So you gave a great short explanation of relativity. But someone noticed that the image looks more like an oval than a circle. And is that because the angle of the telescope or what?
It's where the star, so the star, there's a little area, like a sweet spot where the star can be, where you actually get this sort of ring-like. And if you're slightly off ever so much, you can see more of like a oval shape, and there'll be maybe breaks in the ring, just because it's being lensed, but it's just being like slightly off the center ever so slightly, and that sort of gives you this oval ring.
All right, very cool. Jack, age 8, is curious, is the oldest star that Hubble found also the farthest star that Hubble has found?
Yes. So in terms of age and distances, they sort of go hand in hand. So we are not just looking out really far, but we're also looking back in time. That means that light from that star has taken 12.9 billion years to eventually reach us today. So it has traveled all that way. So when we look at it, we're looking at it when it was alive. It's probably not alive. It probably has exploded now, but we are looking back into the past. And that's because it takes light so long for it to travel all of that distance in order to reach our own eyes. And so yes, it is the furthest. So when you hear something that's really old, also think about something that's really far away, because it has to travel to get to us.
Very cool. So how much of what kind of fuel keeps JWST going for so long?
Oh man, we're getting into the technical questions here.
Or is it solar?
Well, we want to keep the telescope cool. I don't know if it has solar panels, but we do want to keep JWST cool. So we probably don't want to absorb too much solar radiation. Fuel. I actually don't know that answer off the top of my head. I'm going to say rocket fuel, and we'll leave it at that for the time being. But that is a very good question, and something that I guess I need to look into as well.
All right. Would JWST be able to scan into the Oort cloud and maybe find the mysterious planet 9?
I'm sure it will try. So yes, I'm sure it will try to look for it. One of the tricky parts that we are going to run into with these planets is that even in our own solar system is, so the bigger you are, the easier it is for you to retain heat, right? Because it takes a lot, you have a lot of heat to begin with, and then it takes a lot longer for you to cool down. Smaller you are, the less heat you're able to retain. And so you're not as bright in the infrared because you're a lot colder. And so there's probably some question as to if this mysterious planet 9 exists, is it bright enough that we can easily detect it? And also we're scanning a very vast area. I know it seems really small, and we're trying to look for like that motion in the planet, which would tell us that it's planet 9. So it's going to try, is my guess. I don't know if it will, but I'm kind of hopeful. It would be nice to actually have an answer to that question.
Very cool. Will it be able to see the Oort cloud?
So yes, I use that with like a great, like take that. It will look at the Oort cloud. Another tricky part again with the Oort cloud is we're talking about cold planet objects, cold, tiny, small objects. And so they probably don't have that much heat. So they are probably not very bright in the infrared. So maybe I'm not really sure, but I don't know if it will be able to see that much of those.
All right. And here's a very important question. How will all of these exoplanets be named?
So we don't get to name. So there's already a naming convention. And that is that we name planets based on the name of the star. And then we add a letter to it. And the letter is, for the first planet we discover in a system, is B, and then it's C, and it's D. And so if you see a planet with the name, say HD 80606b, that means the star's name is HD 80606 and B means it's the planet. We're not very, we don't give them really awesome names. But that said, we can give them nicknames, and that has been done for several planets. So I got to nickname my super puffs the cotton candy planets, which was kind of fun. So if you can get a nickname to stick, then that means you get to give them a nickname. So that's kind of fun. But yes, most exoplanet names are very boring. Not that fun.
For now.
For now.
So what would be, I just lost this question. I'm going to find it. What might be 3 of the most critical aspects of exoplanets that we think might allow them to sustain life?
Oh, there's so much debate on this too. So we know that, I'm going to go from my opinion, and I'm sure that if I have some of my colleagues are watching this, and I'm sure that they will comment to me on this tomorrow. But I would say one big thing is that you need to have a planet that has an atmosphere. I would say to sustain life for a long period of time, and the atmosphere needs to be stable for enough time. That said, that means that you also need to be around a star, far enough away from the star that the star isn't active. So these small stars called M dwarfs, they're really cool, which means we have to move that so-called habitable zone where liquid water exists much closer to the star because it's so cold. But as you move closer to the star, it means that when a star flares, it's more likely for it to hit your planet and strip the atmosphere away. So that's another thing that you would probably need for life. And there's actually debate whether any M dwarf planet could retain an atmosphere and then retain life. And then the last thing I would say, there's some debate about a magnetic field. A lot of people suggest that a magnetic field diverts that flare, those particles away from your planet, which keeps your atmosphere from being stripped. But I've also seen studies that say that a magnetic field, if you have particles that get trapped in the magnetic field, that magnetic field then tunnels those particles into your atmosphere. Because remember, the magnetic field goes around your planet like this. And so it can actually funnel those high energy solar particles into your atmosphere and cause stripping. So I'm not sure, but I would have to say having an atmosphere is important, at least life, and then not being too far or too close to your star. And of course, we can get into the whole debate of whether you need liquid water or not. If you want life as we know it, probably need some liquid water, but who knows if that's actually needed for life.
All right. So these are questions JWST will be able to answer, right?
Yes. We are going to at least try.
Yeah, great. So Charlie H5 is curious, how does the James Webb Space Telescope see infrared light?
That is good. It is because of the cameras that are on board. So think about taking a picture with a red filter. So have you ever taken a picture where like the whole picture sort of looks a little red tint or green tint or a different color? And that is because that filter basically filters out all the wavelengths of light except for that color. I might have that reversed in my head, but the key thing is the filter is allowing you to only isolate a certain wavelength of light. So infrared, we put in cameras that have a detector that is very sensitive to only a certain wavelength of light, and we can tell it what wavelength of light we want it to be sensitive to based on what it's made of. And so I know that's a little hard and tricky to think about, but let me think about a better way of answering that. But essentially, it's because this detector, we're telling it that with the elements or with what it's made of, we're telling it that we only want it to look at this certain wavelength of light. That's a good question. That is tough to explain. Think about that.
I did a great job. So is that oldest star that Hubble just found, is it still there, do you think?
We're pretty sure that star has probably exploded. So someone once told me that massive stars are, and let me see if I get this right, are the rock stars. And I'm so sorry to use this, but live fast. Well, let me just ignore what I just said. Let's just say these massive stars, they use up their fuel very quickly and they tend to die young. And yeah, so ignore the rock star analogy. That was what was told to me and something I always remembered. But they use up their fuel very quickly because they have to maintain this giant gravity that they have. And so they have to burn a lot so that they don't crush themselves. And eventually they run out of fuel and eventually explode. And the star has probably turned into a black hole by now. So our guess is if you were to look at it today, you would probably actually see a black hole there instead.
All right, but you'd have to get close enough to be able to see it.
Yes.
All right.
Or potentially have something that's lensing around that thing as well.
Mm. So since the JWST heat shield has to remain between the telescope and the sun, does that limit the directions and parts of space we can point it at?
Yes. Yeah. So over the course, we can't just point it at anything. We have to sort of follow Earth's orbit as well, so that we're always having the sun shield with the sun behind that. So you can't just look at the entire night sky at any moment. We actually have to also plan our observations to look at the area of the night sky that always has the sun towards JWST's back, essentially.
All right. And here's a question about Jupiter. What was Jupiter not doing? Was it not spinning fast enough? Does it not have enough gravity? Why did it not become a star?
Jupiter actually just does not have enough mass to start burning fuel in its interior. It actually needs to be quite a bit more massive, something I believe like 13 times more massive in order for it to have ignited and at least burned something in order to make it either a star or what are known as brown dwarfs, which are something in between a star and a planet. So yeah, Jupiter just couldn't get the job done when it was forming.
Oh, wonderful. All right. Well, I think we're about getting down to the end of our presentation. Do you have any wonderful final thoughts you'd like to leave us all with?
Oh, put the pressure
I mean,
on.
you just spent an hour sharing your thoughts.
Yeah, I just want to thank everybody for coming. I had a wonderful time answering your questions, and stay tuned with what JWST can do. And yes, thank you so much for spending this hour with me and hearing me talk about JWST. I hope everybody has a wonderful night.
And thank you for presenting. It was a really wonderful presentation. And I had a great time for sure. And everyone, we hope that you will join us next month on April 27th for our next 60 Minutes in Space. And everyone have a wonderful evening.
Thank you.